So we are studying the, so to say, intensity transformations and spatial filtering is what we are trying to do. So in this we see what is known as a very important thing, which is known as the histogram. Okay, so what a histogram is, how histogram is used for the transformation purpose, and how it can do the filtering, the what you call image can be enhanced using this is what we will try to see. So the histogram processing will involve first histogram equalization, then we have what is known as histogram matching, local histogram processing, and using the histogram statistics for image enhancement. We'll see how much we can cover. Might be we can cover histogram equalization only today, and then might be tomorrow's class we'll take up the histogram matching. So first of all, histogram is nothing but h of rk equal to nk, where rk is the kth intensity value and nk is the number of pixels in an image. So if you have an image, okay, if you have an image, then within that image, how many pixels have a particular intensity value? The intensity value might be 0, 1, 2, 3, till might be, if it's an 8-bit intensity which you are considering, till 255. How many pixels have 0 intensity? How many pixels have 1 intensity? How many pixels have 2 intensity? How many pixels have 3 intensity, and so on, till how many pixels have 255 as the intensity value, if you consider the intensity being represented by a 8-bit value, and that gives us the histogram. So the plot for the RK versus the HRK, that is NK, is going to give us the value of the histogram itself. So on the x-axis you will have RK, that is the intensity value, and on the y-axis you will have the NK, the number of pixels with that intensity value. So plotting that will give you a histogram. So then we can go for a normalized histogram, wherein we'll try to write P of Rk equal to Nk by Mn, where M into N are the number of pixels in the grid. In the image, M will be the number of rows and N will be the number of columns that will be there in the image. So Nk is the number of pixels in the image of size M cross N. Size of the image is M cross N, and Nk is the number of pixels with the particular intensity value Rk. So for example, a histogram might be something like this. So we have here the image and its histogram over here. So you can see that this histogram is more black. So it is concentrated onto the left hand side of the graph. It's concentrated to the left hand side of the graph. Might be from, if you consider this as 0 to 255, so approximately 50, 50, 50, 50, 50. So it's 50, 100, 150. This might be 200, and this might be 255, whatever you take it. So this will be somewhere around, it is concentrated. This, what you call the, intensity of the pixel is concentrated somewhere between, the value which corresponds to 10 might be till 70. 10 till 70 only for this. Now coming to this side, this is more of white. So therefore, black is less in this. So therefore, it's concentrated onto the right. The histogram is concentrated onto the right hand side. It's concentrated onto the right hand side. Now this particular image has the concentration somewhere in between. Might be from 100 to 140 or so. 100 to 140 or so, you have the concentration of the histogram. Whereas if you see over here, this is an image which is using the full range of the, so to say, the histogram. Okay, the full range of all the intensity values. from 0 till the large. So you can see that, it's all distributed. Might be some peaks are there at some particular points, but overall the distribution is quite, good enough for this image. So this is an image which good contrast. Generally, we call this as, this is an image with good contrast. This is an image which is more blackish. This is the image which is more whitish. This is the image which is more, grayish. And this is image which has better contrast with, good distribution of, the, so to say, the, intensity being distributed between the whole range. So better contrast image is this compared to all this. So we would like to have a better contrast image so that, it will be visible better to the human eye. So at the end, our job is, if you have these images, then we should try to bring it to this level. So we have the histogram equalization. Equalization just means trying to spread it as much as possible. So the intensity levels in an image may be viewed as random variables in the interval 0 to L minus 1. L minus 1 will be 2 to the power of 8 minus 1 might be if you are using 8-bit. If you are using 16-bit, then it will be 2 to the power of 16 minus 1. If you're using 24-bit, say for R, G, and B, you are taking 888, 38-bit, signal intensity for each of the color, then it will be 2 to the power of 24 minus 1 will be the value of L minus 1. So let PRR and PSS denote the probability density function of the random variables S and S, R and S. So R might be for the input, S might be for the output. That is before the equalization and after the equalization. Okay, PRR is probability distribution before the equalization. PSS is probability density function after the equalization for the random variables R and S. So this is the original one, the result of applying, A is the arbitrary PDF which we have, and once we apply a proper transformation, we might get a transformation which is like this, which is having almost same or equal intensity. Okay, so result of applying the transformation in the equation 3.34 to all the intensity levels are, so resulting intensities, yes, have a uniform PDF. We would like to have uniform PDF, independent of the form of the PDF of the R's. So this is, not uniform, whereas this is uniform in the whole of the range from 0 to L minus. So this is a more ideal situation where we would like to have this, but we might not get exactly like this, but somewhere nearer this. But our aim is getting this from this. So for that, we do the transformation, which is S is equal to TR. R is the input image, S is the output image for the range of values of R between 0 to L minus 1. So TR transformation should always be, strictly monotonically increasing function. This transformation should always be strictly monotonically increasing function in the interval 0 to L minus 1. So 0 T of R less than L minus 1 for 0 less than R less than L minus 1. So these two are, monotonically increasing. This is, here monotonically increasing, showing multiple values can map on a single value, but strictly monotonically increasing is this. Okay, strictly monotonically increasing is this continuous. There is no constant here. For a single value of SQ is there for multiple values over here of R, RK, or R, you can see over here. For different values of RK from here to here, you have, same value of SQ. Okay, so this is not monotonically increasing, but still it is monotonically increasing. But this is strictly monotonically increasing function, wherein you can see that one input point will have a one-to-one mapping with the output point there. So this is a one-to-one mapping between the R and S. So corresponding to this, we have the TR is continuous and differentiable. Whenever we say that TR is, monotonically increasing, and also it is continuously, continuous and differentiable, then we will get PSS ds is equal to PRR dr. This should be the condition which should be satisfied for continuous and differentiable. One is strictly monotonically increasing. For strictly monotonically increasing, we'll have it as continuous as well as differentiable. Hence, we will have the equation which is PSS ds is equal to PRR dr. So the transformation now, S is equal to R will be equal to L minus 1, integral 0 to R P R W dW. The full-fledged transformation from R to S, which will give S is equal to TR is equal to L minus R, 0 to R P R W dW. So ds by dr will be equal to dtr by dr. You can differentiate this equation which is given over here. If you differentiate this, then you will get this as L minus 1 d by dr integral of PRW dW. So that will turn a differentiation and integration will cancel, and effectively we'll get L minus 1 PRR because limits here are 0 and R. So therefore, we will get the PRR over here because differential and integration will cancel, and this W will become R. So therefore, the value of PSS from the earlier expression which we have written over here, from here, okay, from this you can write the PSS is equal to PRR dr by ds. PRR dr by ds, that is PRR divided by ds by dr. ds by dr we have calculated here as L minus 1 into PRR. PRR and PRR will cancel, and we will get the value here as 1 by L minus 1. So this is a constant value. PSS is a constant value, and that is what is shown in the figure over here. So this is PSS is a constant value throughout when S takes the value 0 to L minus 1. So that's what we have got there. Okay, this is the constant value which we have. Similarly, we can take another example. Suppose that the continuous intensity value in an image have the PDF PRR is equal to 2RL minus 1 square between 0 to L minus 1 and 0 otherwise. Find the transformation function for equalizing the image. So earlier we had taken some value there. So now we can take the value which is PRR is equal to 2R divided by L minus 1 whole square to 0. So how does S look like? Okay, how does S look like is what we can try to do it. So again, you can apply the same formula, that is L minus 1 integral 0 to R PRW. So in place of PRW, we should try to write here 2R by L minus 1 for PRR. So then naturally in place of R we have W. So therefore we'll get this type of equation L minus 1, this type of equation which is L minus 1 0 to R 2W by L minus 1 square dW. So this is a constant. You can just take it out. It will be 1 by L minus 1, and 2W, if it is integrated, you will get W square or W square, and if you substitute the limits, it will become R square. So we'll get R squared by L minus 1. Okay, we'll get R squared by L minus 1. So thus we can get the expression for the value. Now for the discrete value case, so until now what we considered was the continuous case. For the discrete value case, you will have the transformation Sk is equal to Trk equal to L minus 1 multiplied by sigma. So now in place of integral, we have here in the discrete case the sigma. If you remember digital signal processing also, right, or even for that matter Fourier transform and Fourier series. Fourier transform is continuous, That is why it is integral. Fourier series is discrete. That's why we have the summation. Same way, here this is the continuous case and this is the discrete case. So for that, you can try to write if PR or J is Nj by Mn. You can try to write like this, L minus 1 Mn and sigma of Nj. So if some expression is there for Nj, you can substitute it and you can get it. Now let us take a full example of a histogram equalization. Suppose that a 3-bit image, we have a 3-bit image that is L equal to 8, 2 to the power of 3 will be L equal to 8. L is 2 to the power of 3, that is 8. Of size 64 into 64 pixels. So that is M and N is, 64 and 64. And so Mn will be equal to, M into N will be equal to 4096. Has the intensity distribution shown in the following table. So this is the intensity distribution shown in the table. Get the histogram equalization transfer function and give the PSSK for each SK. So we have here R0 for R0 equal to 0, that is, the K equal to 0, the value of N0, so to say, is 790. For K equal to 1, the value of N1 is 1023 and so on. So we can get from this the PRRK as Nk divided by Mn. Mn is here 4096. Now this L equal to 8 gives us 0 to 7. This L equal to 8 gives us 0 to 7. If we have, say, what you call 4-bit, then L will be 16. So therefore we'll have R0 till R15. If L is equal to, if you have an 8-bit image, then L will be equal to 2 to the power of 8, that is 256. So therefore, the values of RK will take from 0 to 255. And for that, what will be each value of Nk is what we need to find out. So in this case, only 3-bit. So therefore, R0 to R7 and Nk will be the number of pixels which are having each of this intensity. Now, if you divide each of this quantity by 4096, you'll get 0.19, 0.25, 0.21, and all that. And if you add all these, you'll get 1. You'll get the sum of all the probabilities together will become 1. So same thing is repeated in the first figure there. And now we can find S0, S1, S2, S3, and so on. So S0 will be TR0, discrete case. This is discrete net case, not continuous case, because we are taking 0 to 7. 7 into sigma j equal to 0 to 0 PRJ. So this quantity is, PRJ will be equal to 0.19 for R0. Okay. PRJ means P of 0, 0. Okay. P of 0, 0. R is 0, K is 0. 7 into 0.19 equal to 1.33. Then, because this value 1.3, we are talking about discrete case, we are making the rounding off 1.33 to the value 1. Next, we go for TR1 equal to 7 into sigma j equal to 0 to 1 PRJ. So j equal to 0 to 0 will give us P0, PRR0, PRR0, whereas here it is 0 to 1, so that means both these two together added. So 7 into 0.19 plus 0.25 equal to 3.08, and this is to be rounded off to the next value, which is 3. Okay, rounding off is what is done. So the value 0.33 is rounded off, less than 0.5. This is less than 0.5, therefore we have 1. 0.08 is less than 0.5, therefore it is 3. Similarly, you can try to calculate the value of S2. S2 will be 7 into 0.21 plus 0.25 plus 0.19. So together it will give the value which is 0.65. 0.65 into 7 will be 4.55. 4.55 is rounded off to the 5 value. S3 will be all these 4 added together. That will be 0.81. 0.81 into 7 will give you 5.67, and that is rounded off to 6. Then S4 will be 0.8, might be 9.89 into the value which is 7. That will give you the value which is that will give you the value which is the value which is here, the value which is again 6.23, that is 6. Similarly, S5 you can calculate, it will give 6.67. S6 you can calculate. All these are to be rounded off to 7. So therefore, S0 will be 1, S1 is 3, S2 is 5, S3 is 6, S4 is 6, S5 is 7, S6 is 7, and S7 is the value 7. So all that is, the PRRK is plotted over here, SK versus RK is plotted here, and then we can try to plot the value of P of SK over here. So thus, this is the equalization. You can see that in the whole of the range, it is decreasing over here. It is decreasing, the probability is decreasing, whereas here, the probability is more uniform now. The probability is more uniform now, okay, for the values from 0 to 7, right? For the values from 0 to 7. So really speaking, if you see over here, we have not, what you call 1 takes the value this one, 3 takes the value this, and 5 takes the value this. So we have this distribution almost uniform. So equalization is done over here. So original histogram, transformation function, and equalized histogram. So if this is the image which is given to us, which had an histogram which is totally on the left hand side, then after equalization we'll get this, and that is almost uniformly distributed. And if this is the image which has the histogram totally on the right hand side, which is more whitish than black, then we'll get after equalization this figure, which is again, you can see that uniform distribution is there. And if you have this, which is in histogram, which is exactly in the middle for this, figure, which is more, typical grayish, then after equalization we'll get this, and that like this. And this is, already we have quite good, contrast. And again, further, if you try to apply the what you call the equalization, you might get a function which is something like this, which is again quite well distributed over here. So thus, equalization will give you the what you call good contrast, image. For transformation function for histogram equalization, 1 through 4 were obtained from the histogram of images from top to bottom. That means whatever we have written in the 4 figures over here. In the left column of the figure 3.20 using the equation 3.38. So 4 different ones are given over here. The transfer function for the histogram equalization. Okay, for 1, 2, 3, and 4. So almost you can see that this is, 4 is almost linear. Earlier also it was, what you call well distributed. Now also it is, after transformation also it is well distributed. So therefore the slope is almost for this one, whereas the slope of this is quite high for each one of this, right? So we have some more, image from the Phoenix lander A, which is there over here. Then you do the histogram equalization. So this is more blackish. That means you have the concentration of the histogram onto the left side. If you do the histogram equalization, we'll get this type of figure, and its histogram is, you can see, more evenly distributed across the whole of the range of values of RK. So is histogram equalization always good? Is a question which arises in the mind. We see that it is not so. In some cases, histogram fails. So for this, we try to do, whenever histogram fails, we try to do what is known as histogram specification or histogram matching. Okay, so histogram specification or histogram matching is an extension of the histogram equalization. Okay, so we'll take this up in the next class. So if you have any doubts, you can ask.